Welcome to the NYU Tandon School of Engineering. Those of you who know me or who have been to any of the seminars know that I'm fond of a quote attributed to Albert Einstein. The important thing is not to stop questioning. Curiosity has its own reason for existing. As researchers, I think we are all naturally curious people, and we share a drive to answer previously unanswerable questions and discover new things. So thank you for both your presence and your curiosity. Thank you as well to Tandon Executive Dean Juan de Pablo, who also serves as NYU First Executive VP for Global Science and Technology, and Senior Vice Dean Aray Adil for their support, and to my own Department of Electrical and Computer Engineering for hosting the seminar series in Modern Artificial Intelligence. It has been among the greatest honors of my career to see this series evolve into a significant event in the AI world and a vehicle for unifying scientific communities around the influential research ideas of today that can have a major impact tomorrow. It's thus with great pleasure that I introduce today's speaker, who truly exemplifies intellectual curiosity and impactful research. Mark Schmidt is a professor in the Department of Computer Science at the University of British Columbia. His research focuses on developing faster algorithms for large-scale machine learning and exploring the applications of machine learning. He is a Canada Research Chair, Alfred P. Sloan Fellow, and Sir Arthur B. MacDonald Fellow, and CIFAR Canada AI Chair with the Alberta Machine Intelligence Institute. In 2018, along with Nicolas Leroux and Francis Bach, he was awarded the Siam-Moss Lagrange Prize in Continuous Optimization. His presentation today asks, why does Adam work so well for LLMs? And can we find optimal per variable step sizes? I know we're all curious about the answers, so without further ado, let's warmly welcome Mark Schmidt.
Okay, can people hear me in the room and online? Yeah, okay. So I'm Mark, thanks Anna for the introduction. So today I'm going to talk about those two questions. So the work I'm going to talk about today is primarily led by my former PhD student, Fred Kunstner. He's now gone to be a postdoc in Paris, and he'll be on the job market probably next year. Just absolutely outstanding student. You'll see all the cool stuff he did today. But there was also a lot of other collaborators, so I've just listed the collaborators for each of the three projects. A bunch of undergrads and a few other PhD students and another faculty member at UBC. All right. So I probably don't have to tell you this in this seminar, but machine learning is changing the world, right? You can automatically caption your Zoom. You can pay your French taxes if you don't speak French very well. You get your passport scanned at the airport. You can see where to hit pedestrians in your car. It's changed the NBA. We've now realized that 3-pointers are worth more than 2-pointers, so maybe we should shoot a lot of 3-pointers. You can do animated characters, fold proteins. You can make Johnny Cash sing Barbie Girl. You can cheat at StarCraft. You can cheat on your homework, or you can put artists out of work. So lots of cool stuff. And there's tons of potential new applications, right? Machine learning is not going away. We're going to keep being obnoxious and going and annoying people in other fields over and over and over again. So if we make some fundamental advances in machine learning, we can potentially affect many different applications. And there's no better example of this than ChatGPT. You know, I didn't used to go to the gym and hear people talk about machine learning on the treadmill next to me. It's really quite different than it used to be. All right, so what does learning mean? In most modern machine learning models, when we say we're doing learning, what are you doing? You're solving a numerical optimization problem. What does that mean? You're trying to minimize some sort of cost function in terms of some numerical parameters. There's two optimizers that really have taken over from empirical work. One of them is called stochastic gradient descent, or SGD, usually with something called momentum. And the other one is Adam, which may or may not stand for adaptive moment estimation. And there's also many variations on this. There's like 100 variations. And I would argue that we actually don't really have a good understanding of why these work. We use them because we find that they've worked in a bunch of important applications. SGD and momentum has some justification in some very, very simplified settings, but not in the ones we actually use them for. And I would argue we basically have no theoretical justification for why Adam is faster than SGD sometimes. So what I want to talk about today is why do we think Adam is faster than SGD for language models? And And could we design a theoretically optimal adaptive method once we think about what the adaptive method might be trying to do? Okay, so that's my overview. I'm going to jump right in. We okay with that? All right. So here's stochastic gradient descent. Just to give you my notation, I want to minimize the function f. It has parameters w. I'm going to generate a sequence of iterations, wk. To generate the next iteration, wk plus 1, I subtract a step size alpha. Okay, so hopefully we're back on. All right, momentum rate, that's SGD. It's quite simple. Setting alpha and beta are super annoying, but that's what we're with. And then here's Adam, which is a little bit more funky. I've tried to annotate it a bit, but I don't think we fully really know what's happening here. So we've got this step here. Mu k is basically our momentum, and we do this momentum update. We take this convex combination of our gradient and the previous momentum. Vk is basically keeping track of our gradients squared, some running average of our gradients squared. And then we put these Vks into a diagonal matrix and multiply the inverse of that by our momentum. And so we've sort of got a momentum, we've got this per variable step size, and we've got maybe this thing that looks like a second order update, maybe. So sometimes this is interpreted as a Newton-like method, especially if you're not being very careful, because this looks a little bit like Newton's method. Maybe that's like a gradient and that's like a Hessian approximation. But if you remove the averaging, what is it actually doing? It's doing what's called sign descent. You take the gradient. For elements that are positive, you use +1. For elements that are negative, you use -1, and you just do that. And sign descent is really a first order method. This is not a Newton-like method. So this idea that it's Newton-like is not really consistent with this notion that it's sign descent. And I would say we really don't have a good understanding of when and why Adam works. I just wanted to show you that. The actual details are not going to be super important for the talk. I just wanted to show you what it looks like. So Adam is one of the most cited works of all time across all fields. We've recently passed 200,000 citations. That's kind of bonkers. This is like approaching like top 10 all time. I think it's actually in the top 10 all time most cited papers across everything, like more citations than PCR, for example. So Adam does not converge in general, and it can fail on some simple problems. So the algorithms, the sort of test functions you get out of your scientific computing textbook, you try running Adam on that, it might just fail. Might like look good for a while, and then it might like diverge or something funky like that. So Ben Recht has this quote that the most cited paper in all of optimization proves an incorrect theorem with an unparsable convergence bound. We really don't quite know what's going on. There's been lots of algorithms that try to fix the convergence, but when you try and fix it, you make it slower. And so you don't want to like throw the baby out with the bathwater. We don't want to fix it, but miss the whole point of reasoning using it. We're fast. I'll just finish the slide and then we'll. Okay, but on a lot of difficult problems, there's no other algorithm that consistently beats it. The only things you can do to beat it are you do minor variations. And so, for example, I went last week to San Francisco to Facebook, where they announced this results of this AlgoPerf competition. It's like enter your algorithm, and we'll see which algorithm actually works the best across a bunch of problems. And they had a baseline method, which was an Adam variant where they tuned the step size reasonably. And there was only one method, one submission that beat the baseline. And what was that method? It was also a version of Adam where they chose the step size a bit more cleverly. So this is where we're at machine learning.
How much faster is Adam than SGD?
How much faster is Adam than Okay, back to microphone number 1. Okay, so here's our question that I asked Fred well, I don't know if I asked him to do this, but he thought about it. Why is Adam faster on language but not vision? And this is consistently seen across a bunch of data sets. So let's think about possible hypotheses. The first one is the reason I ignored Adam for a long time. Because on over-parameterized models, these are models where we can fit the data set exactly. We know that SGD with a constant step size is almost impossible to beat. See my other papers for why that's true. So Adam is kind of like using a constant step size. It doesn't really converge because the step size doesn't go to 0. But that might explain why Adam is fast, but it doesn't explain why Adam is faster than SGD, because SGD would also be fast in this setting. There's been some papers that basically said, well, Adam has more hyperparameters to tune than SGD. I've got 3 step sizes to play with instead of, well, possibly more depending on how you look at it, instead of just 1 or maybe 2. And that's true, there are more hyperparameters, but there's more hyperparameters on vision problems just as well as on language problems. Maybe Adam is approximating second order information. Maybe that's true, but why would the sign-like update do this for language models but not for vision models? Okay, here's a nice one. Adam co-evolved with network architectures. We sort of made Adam the default optimizer, and then we only explored networks that worked well with Adam. Okay, cool, that's true. But again, the vision architectures have been changing too. So why is it that we only saw this coevolution in language and not so much in vision? And then here's my explanation in light of all these things that don't make sense. Maybe Adam was sent from the future to speed progress on language models. I don't have any evidence against that. All right, so here is a nice hypothesis that was proposed by some folks from MIT. They made this observation that if you look at the gradients when you're doing stochastic gradient, and you look at how far away they are from the true gradient, the vision and language models produce something different. On the vision data set, you tend to have something that's approximately like a normal distribution, something nice. On a language data set, you get these heavy tails. And so on language, you have much more nasty noise. And so logically, you might think that Adam works better because it handles heavy-tailed noise better than SGD. And they proved that it does handle heavy-tailed noise better than SGD, although that doesn't necessarily mean that that's the reason for the performance difference. So can we actually test whether that's true by doing an experiment? And so how do we do that? Let's try and remove the noise. How do I remove the noise? Instead of just training on a small mini batch, I'll train on really big mini batches. And in fact, if I go to the whole data set, then I have a deterministic update. There's no noise anymore. So if that happens, then I should see SGD and Adam performing similarly. And that's exactly the opposite of what happens. As the noise gets smaller, as you get less and less noise, Adam gets even more and more of an advantage. The gap grows bigger. So theoretically, removing the noise, if the noise is the issue, should reduce the gap, but the gap actually gets bigger when you remove the noise on the language problems. So that doesn't seem like that's the right hypothesis. Okay, are we happy with that? Okay, so the gap really cannot be exclusively due to the noise. Adam still provably helps with noise. It just doesn't seem like that's the main effect here. So here's the new hypothesis that Fred came up with. He called it heavy-tailed labels. I kind of want to change that name now that I've been talking about it more and more because I find it gives some confusion, but let's go over what I'm talking about. Vision data sets traditionally have balanced labels. So if you look at the ImageNet data set, you basically have around 1,000 images of cats, around 1,000 images of dogs, around 1,000 images of cars, and so on for all the different labels. The language data sets, you're not predicting that, you're predicting individual words, like the, cat, dog, building, whatever. And words are known to have a heavy-tailed distribution. So some words like the appear very, very often, and some words, like pick your favorite really long word here, basically don't occur at all. And so, yeah, most words are rare. Could that help explain the gap? This distribution of the labels. This has nothing to do with the noise. It's actually sort of what different things we want to predict. So it's a very nice plot that's been done here. Let me talk through it. here's gradient descent, here's Adam. We're going to divide up that loss based on the class frequencies. So this line down here, that's the 10% of the data from the most frequent classes. This is words like the. This is the 10% of the data from the least frequent classes, the classes that are seen not very often. It's still 10% of the data, right? There's not less data here. It's just data from classes that are less frequent. And if you look at what happens, SGD learns the very frequent words quite fast, and then the words that don't happen very often are learned very slowly. And again, it's not because you're not seeing many of these things, it's just there's so many individual words there that are rare. And if you look at what happens with Adam across classes, it tends to learn all the classes quite fast. So SGD tends to make slow progress when you have rare labels. And if most labels are rare, SGD is going to make slow overall progress. Whereas Adam is making similar progress on all labels. So if most labels are rare, Adam can still be making progress. Yeah, go ahead.
What's surprising though is the yellow goes down faster than the green.
Yeah, this part is kind of funky. I don't have great intuition for the ordering and so on, but I guess the main observation is that that doesn't happen. Go ahead. So we're not measuring performance divided by class. If you add up these 10 lines, you get this line. If you add up these 10 lines, you get that line. It's just each one is just 10% of the data. I've just grouped them in a certain way. Okay, so we observe something, it seems to correlate with what's happening, but let's try and be really scientific. Let's not try and do like the heavy-tailed noise hypothesis and then have someone do a simple experiment and show that it isn't true. So how can we try and either support or refute this hypothesis that the heavy-tailed label is an explanation of the gap? Well, what if I made a computer vision data set that had that weird label distribution? So they took MNIST, our classic digits, and they added a whole bunch of new classes to it. And these are classes that are not super hard to learn, but it was set up such that I think it's half the data is now from a rare class. And so now, MNIST, normally there's not so much difference between SGD and Adam, but in this version with heavy-tailed labels, you now get this gap between SGD and Adam. And you can see again, the non-rare classes are easy, the rare classes are hard, and for Adam, they're both not that bad. Could we even make a linear model? I can make that same distribution of labels on a linear model. And so you can do the same thing. You can make a heavy-tailed set of classes, and you find that Adam is going to work better than SGD even on a linear model. And that's really nice for me as a theoretician, because we know how to prove stuff about linear models a lot more easily than we do on deep neural networks. So if we can reproduce this phenomenon in a linear model, that gives hope that maybe we can have a nice theory that explains where and when and why Adam works. You can also go in the other direction. Could I make the gap disappear on language models by taking the class labels into account? And the answer is kind of. So what you could do is you could upweight the loss of the low frequency examples, feed that to SGD, and that makes SGD perform a lot better. The only problem is you've actually changed the loss function. So you're now solving a different problem that really focuses on getting rare words correct. So if you interpolate the data, that's fine, but on a normal language data set, this isn't actually a good idea, but it does indicate that we could design algorithms that make SGD reduce this gap. Okay, so I think that's nice, right? I mean, it's not a theorem, but it's like a strong evidence that this is at least a real thing that optimization has been missing for a long time. Do we have thoughts or comments on that? All right. So one question you might ask is it seems like the sign is kind of a good curvature estimate in this setting of heavy tail labels. Why would that be true? If you look at some norm of the gradient and some norm of the Hessian as it goes along, and you look at this for the different class labels, at the start, they're not really related to each other, but as you go along, for many data sets, they become very correlated with each other. So the gradient and the Hessian are becoming correlated with each other. What does that mean? That means if I divide the gradient by the Hessian and make the dimensions match somehow, I basically get the sign. I get plus and minus 1. Another factor because Adam only uses a step size per variable, is what does the Hessian actually look like? It looks like as you go along, the Hessian becomes very diagonally dominant. So just using a diagonal scaling, just using the sign is probably a very sensible thing to do. That may not be true for every data set, but for language models, it seems that just Adam happens to be like the perfect algorithm to take advantage of what the Hessian actually looks like. Again, sent from the future. Okay, we were trying to do some theory, so we tried to find a simpler algorithm than Adam to analyze. And what we found is that as long as your batch size is large enough, doing the sign descent and adding momentum is a pretty good approximation for what Adam does on these heavy-tailed label problems. So if you just do that algorithm, you get pretty similar at large batch sizes to what Adam does. And this algorithm is less scary to prove things about than the Adam algorithm. One thing I'll note is people also, a lot of explanations for why Adam work involve saying it like clips the gradient or something like that. But if you just clip the gradient and use normalized SGD, that really doesn't seem to address the heavy-tailed thing in the same way. Something to note is after our paper came out, Google Brain sort of symbolically discovered the line optimizer, which is basically something like this. Okay, so can we prove that sign descent is faster than gradient descent? Not in general. In extremely, extremely sad, very restricted setting, they did actually prove that that was true, at least for the gradient flow. So gradient descent has this sublinear rate where pi k is the class label distribution. And sign descent has this linear rate where C is the number of classes. And so in summary, in a very simplified setting, excuse me, gradient descent has a sublinear rate, and the worse, you get bad constants for rare classes. Normalized gradient descent has a linear rate. The class distribution is maybe not so obvious there. I should probably remove that statement as Fred said. And sign descent, you get a linear rate, which is better than sublinear, and it's also invariant to the class distribution. It depends on the number of classes, but it doesn't depend on how they're distributed, which is really nice. And so at least in a simple setting, we did prove that sign descent is like going to make you go like a lot faster. All right, so some questions you might ask if you're familiar with some of the literature. Am I just describing class imbalance? And didn't the original AdaCrad paper talk about sparse features? If we just reinvented something that already exists? So I would argue these are not the same because those two things can happen even with binary labels. In order to have this heavy-tailed thing, you actually need lots of possible labels. If you only have 10 labels, you can't really do this. You need like hundreds or thousands of labels. So the usual class imbalance that you might see in your machine learning class is 99% of examples are in one class, and then you have 1% of examples in the other class or many more classes. That's fine for SGD because 99% of the time you're doing a good step. It's really only when most examples are from rare classes that you see this weird phenomenon we're talking about. The original AdaGrad paper considered sparse but informative features. That can also lead to a gap. And there's something called graph neural networks that also have a gap that do not have this heavy-tailed thing, but they do have this sparse features thing. So it's another way that you could get this gap. But the heavy-tail labels doesn't really require sparse features. This is really about the output and not what the input looks like. Okay, I think that's the last thing I want to say about the heavy-tailed thing. That was my sort of discussion. Do we have any thoughts or comments?
Question.
Yeah, go ahead.
Supposing that it costs more money to get the rare classes, is there a model you can create that tells you how much, say it costs 10 times more to get the rare classes than the more common classes? Data acquisition could be very expensive. Labeling could be expensive. You say any words about how one optimizes that larger picture?
Yeah. So the question is, what if it's more expensive to get labels or to get examples from the rare classes? Can you somehow optimize that? And the answer is I have no clue. I just haven't thought about it at all. And the stuff we've learned here, I'm not sure helps me answer that question without thinking a lot about it. Sorry. All right. Okay. So if you are sick of experiments and want a really theoretical result, now is the time to wake up. I'll walk over here. So I am trying to get the attention of people who like proving theorems and are interested in like fundamental optimization results. Sorry, I'm ignoring the chat. If people want to ask the chat questions, you can raise your hand and tell me the chat questions. I'm not good at monitoring it in real time. Okay. So Adam and a lot of related methods use a step size for each variable. So canonical example of that might be something like, I take my parameters and I subtract the gradient multiplied element-wise by some vector AK. And so I'm scaling each variable by its own like learning rate here. So the reason we like that sort of scaling and not like a Newton method is we have this O of D cost if we have D variables. So it's still very cheap to use that type of preconditioner, if you will. And it is known that you can be arbitrarily faster with this. So on the problem on the left here, we've got a problem with condition number kappa equals 16. You take your gradient descent class and you see that you sort of get this zigzag pattern. We take the same problem and we do like a diagonal rescaling, which is really what this does. So you just stretch out this dimension, which is what a per variable step size can do. And now it's a lot nicer. You can change the condition number to 2 here. So this is also known as diagonal preconditioning. It has a very large literature. It goes all the way back to like Jacobi's work in 1845. This is in all the numerical linear algebra textbooks. And the name preconditioning I learned from Wikipedia says that goes back to Turing in the 40s. So the idea of preconditioning is not like new in any way. But I want to ask this question. Do we actually have good diagonal preconditioners? Under a very simple notion of what it means to be good. So let's say I have this textbook problem. I have a smooth and strongly convex function. What does that mean? If you look at the Hessian, the second derivative matrix of the function, its singular values are at most L, and they're lower bounded by some number, their eigenvalues are lower bounded by some number mu greater than 0. So the second derivatives are kind of nicely behaved. So that the textbook analysis of gradient descent says that if you run gradient descent for k iterations, and you look at how far you are away from the optimal solution, you'll get basically where you started, the initial suboptimality, times 1 minus 1 over kappa. Kappa is L over mu, that's called the condition number, raised to the power of k. You go down as this like geometric type of sequence. And that's the optimal step size, but we have lots of practical algorithms that perform basically within a constant factor. You'll see you can do this in practice with a factor of 2 there, and I'll show that on the next slide. So this is the classic gradient descent analysis. You might have heard of something called Nesterov acceleration. We can go a little bit faster. In Nesterov acceleration, you replace kappa with square root of kappa by adding a momentum type of term. So how well can you do with an optimal diagonal preconditioner? Well, you basically replace kappa with kappa tilde. What is kappa tilde? It's the condition number under the best diagonal reparameterization of the problem. So you take your variables, you multiply them by a diagonal matrix. If you choose the absolute best diagonal matrix to do that transformation and look at the condition number, we call that kappa tilde. How much better can kappa be than kappa tilde? Is it just square root? Well, it might be worse. It might be the same as kappa, but it can actually be arbitrarily better. So we can get a much more acceleration than we would with like Nesterov acceleration. Now you might ask, does Adam achieve that? And the answer is no. In fact, there's no algorithm that's known to achieve that, at least at the time we did this work. So you can look at Adagrad, Adam, you can take the diagonals of the Hessian, you can do quasi-Newton methods, you can do hypergradient descent, you can even do second order methods like cubic regularization of Newton's method and all that stuff. None of them will actually achieve this rate with the kappa tilde on every step. It's kind of wild. And again, not a new problem. Diagonal preconditioners have been around a long time. Why don't we have an algorithm to do this? Okay, so Fred proposed something called multi-dimensional backtracking. It's the first algorithm to perform within a known factor of the optimal diagonal preconditioner. So we're trying to replace Adam. We didn't get there, but at least we took the first step. Okay, so I want to talk about the classic backtracking before I talk about the more complicated one. So how does that work? You want to minimize a function. You have some guess for the step size alpha, and we're going to assume the initial guess is big enough, that it's bigger than the true optimal step size. And so what you do is you test this inequality. You look at the WK plus 1 you would generate with the current alpha, and you compare it to the previous function value and the size of the gradient and the size of the step size. If that's satisfied, you're good. You just use that alpha. If that's not satisfied, You divide alpha in half, you test this condition again, and you do it till it's satisfied. It's also called the Armijo condition, or at least a special case of it. So if you do that, you get the optimal step size up to this extra factor of 2. I get the same rate as the optimal step size. I just get a factor of 2 here, which I'm not like overly concerned about. There's lots of variations of that exist. I don't recommend that exact procedure. So if you, for example, if you do that for neural nets, it makes what's called the sharpness explode. The size of the weights just gets bigger and bigger and bigger as you go along, and the step sizes get smaller, and eventually you run into numerical issues. So there's other things like the Polyak step size and the Linsky-Mashenko step size. They get you a factor of 4, but they give you some nice big step sizes that adapt to the problem a bit better. There's also something called non-monotone line searches that work a bit better, and they avoid this sharpness explosion. So you can Google that if you want. Okay, so instead of that view on backtracking, we're going to do this other weird view because we want to generalize it to more than one dimension. And so what we're going to do is we're going to think of this as maintaining an interval 0 to alpha max. And I want this interval to contain the optimal step size alpha star. And whenever we make our guess for alpha star is going to be the halfway point of the interval. So we're always going to set alpha to be alpha max over 2. All right. So if that is satisfied, then we've got a step size that's if we satisfy the sufficient decrease, we're happy with alpha, we just go. We've got something bigger than the optimal step size. We got lucky and we can make more progress than expected. If it's violated, what do? We just set alpha max, the new alpha max to alpha, the old one divided by 2. Now we've got a new interval that still contains alpha star because we knew that this one was too big, and we're going to use the new guess. So what are we trying to maintain here? We're trying to maintain that the largest point in our interval is bigger than the optimal step size. The optimal step size is in the set, but we don't want our step size to get too small. I want the step size to always be bigger than alpha star over 2, which will be guaranteed. So here my step size is a little bit too small, but it's never going to be too small by more than a half, because otherwise it would get rejected. So, okay, in practice, you can get lucky and you can use a larger step size than alpha star, but we're just happy with that. We just take the win in that case. All right, so let's try and generalize that to more than one step size. I want a step size for every variable. You can generalize the condition very easily. The Armijo condition is known to have this variation. So you just replace the gradient norm squared with the gradient times the individual step sizes. Okay, that's fine. But the hard part is, how do you search for the step sizes? So I don't just have an interval anymore. I have a d-dimensional space of possible sets of d step sizes. So here's an example in 2D. And you can think of this as I have a space of step size 1 and step size 2. And the optimal individual step size, if they're both the same, is right here. These are the step sizes that are too big. These are the step sizes that are all valid. And what you can see here is, well, the optimal step size is not good because I can make this first step size a lot bigger. So I would ideally like to use a point here where I'm making the second step size a little bit smaller and the first step size a lot bigger to make a lot more progress. So that's conceptually the picture we want, but it's super annoying. Because let's say I find that this step size doesn't work. Well, what does that rule out? What other step sizes can I not use now? The other issue is, where should I go next? Just one point in a d-dimensional space doesn't really tell you much about where to go. The nice thing about the intervals is I just go smaller, but now it's not obvious what you should necessarily do. And then the other issue is, can I maintain this O of D cost? I don't want to use a diagonal preconditioner that's super expensive because that would be kind of missing the point. All right. So one thing you can observe is, if you have an invalid set of step sizes, increasing any step size is still going to be invalid. You really can only go smaller. And that's what you do in 1D. So if you had this interval and you found that that step was no good, you can rule this out. But in 2D, that's less useful, because if you rule out these two step sizes, that means, well, you can't make the first one bigger or you can't make the second one bigger individually, but you might be able to make the first one bigger and the second one smaller or something like that. So where do you search? And then in 3D, it gets even worse. So we've basically got a cursive dimensionality problem here, which is really annoying. So, you don't know whether you can increase one variable and decrease the other. So it's really, really annoying. And I think that's where everybody gets stuck. And then Fred went and thought really, really hard about this and talked to a lot of people. So like, how should we explore this space? So before I say how, I want to talk about this other weird algorithm called hypergradient descent. I'm going to take the gradient with respect to the step sizes. Gradient of alpha. That's just reminding me to wrap up in 5 minutes. And I'm going to do gradient descent on the step sizes. Okay, you can do that. You might think that's original. That's been reinvented many times over the last 60 years. So the first instance of it is 1958. But lots of people have reinvented basically variations on this algorithm. Do gradient descent on the step sizes, call it hypergradient descent. And if I don't think there's anyone in the room who's really got a stake in this, but in some rooms, I would say this is arguably, this method only works in papers. What does that mean? It means, well, it works in the papers that propose it, but then someone else tries it and finds that it doesn't work. And so we're not really happy about that. Well, okay, let's go back to multidimensional backtracking. There's a connection between this hypergradient, the gradient with respect to the step sizes, and that space of preconditioners. And so what is it? The hypergradient gives you a separating hyperplane on the valid step sizes for convex problems. What does that mean? I find that this preconditioner was too big. I take the hypergradient. That gives me a plane that tells me this is where the valid preconditions are. This is where the optimal one is, and it cannot be up here. All of these are invalid. So now you can cut off a huge part of the space in high dimension. You get this half space where you can cut off the space. Now, if you know about cutting plane methods, you should be scared right now because I don't want to store a whole bunch of different planes and have to cut them off because that'll destroy my O of D cost. So the first method they consider is what they call the box method. You get your cutting plane, and then you just find the biggest box that contains the valid region. And so now I can just summarize my area that I'm searching for with D numbers. I can get the O of D cost. And if you backtrack from the biggest point in that box by 2 to the D, you get the first result of this flavor, depending on the kappa tilde. You get 1 over 2, just like with the Armillo case. You get D, which you're not like super happy about. You don't want the dimension to show up here, but we got to start somewhere. And there's our kappa tilde. Very, very simple algorithm. There's a much more complicated algorithm in the paper where you can replace this D with square root of D and still keep the O of D cost with axis-aligned ellipsoids. That's more annoying, but you can improve the result a bit. Does it work? It seems promising. This is a quadratic problem where I can actually compute the optimal diagonal preconditioner by solving a semi-definite program. You would never do that because that's more expensive than solving a quadratic program, but we can see how it behaves. If you look at that box method, so we start it with big step sizes and they get smaller and smaller and smaller. And these blue dots, those are the optimal preconditioners. So it's coming really close to actually finding the optimal as it goes along. And on these earlier steps, well, it might be even doing even better. And the ellipsoid method does even better because it it sort of gets lucky and finds ones that happen to be bigger. And you might say, well, can I do acceleration for this problem? And it's like you can, but you change the conditioner from 10 to the 14 only down to the 10 to the 7, whereas kappa tilde here is 10 to the 2. So it's making a much bigger difference than Nesterov acceleration would make. Okay, going to like a real data set. There's more experiments in the paper, but here's a smattering. So they tried to compare with like competitive methods, and it wasn't always the best method, but it was always like, okay, this ellipsoid method. And I want to emphasize, like, you may have heard of quasi-Newton methods in your scientific computing class. The goal here is the same. We're trying to estimate like a preconditioning matrix, but quasi-Newton methods try and interpolate the gradients to approximate the Hessian. Here, we're not trying to approximate the Hessian. Here, we're just trying to maximize progress. We're just trying to minimize the function as best we can as the preconditioner. So it's like a very different way to do approximate a preconditioner as you go. Okay, so how does this look time-wise? Theoretically, these are all O of D time, so we didn't plot time. You know, if you put a lot of implementation effort in, you can make them all look pretty similar. Okay, so I want to end up with some open problems. We assume strong convexity. I don't know how to do this for non-convex problems because we lose that separating hyperplane property that makes the hypergradient useful. You can probably design some sort of fail-safe to make it work, but I'm not sure how to do it. I think you could come up with better practical implementation details. The only implementation trick they do is they multiply the step sizes by 1.1 after each accepted step so that they can keep try and get bigger. But there's probably more clever things you can do, and you can try and make stochastic versions. You can try and reduce the square root of d factor. One thing you can do is you can get the best of the classic backtracking and the multidimensional backtracking. You can also interpolate between the two. If you like group variables together, you can replace d with like number of groups. There was a recent work out of Stanford where they proposed something called online scaling. They actually went back to the hypergradient descent method and used an online learning algorithm to update the step sizes. And they get a similar rate, but they get rid of the square root of d asymptotically. And so that's kind of nice. It's not clear. There are some lower bounds that indicate that it may not be possible to get rid of it non-asymptotically, but that's still nice. And there's some new non-asymptotic quasi-Newton methods results, which are kind of neat because they're eventually faster than ours, but on the early iterations, they're slower. All right, so let's wrap up. Diagonal preconditioned methods like Adam, they're wildly popular. They're behind your language models. They're behind all sorts of fun things. Their effectiveness does not seem to be due to how they handle noise. It really seems like it's a deterministic optimization phenomenon that we need to understand. On language models, it seems to be largely due to this heavy-tailed labels, where a large fraction of your data sets have rare labels. That seems to be the phenomenon. And we gave this first diagonal preconditioning method with optimality guarantees. Multidimensional backtracking uses cutting planes to rule out sets of step sizes to try and jointly find a good set of step sizes. It's the first like step size per variable method that has any theoretical guarantee in the smooth case, at least. Adagrad has guarantees in the non-smooth case. All right. So finally, thanks for coming to listen, and thanks for hosting me. And hopefully you learned something today. And I guess I'm assuming there's time to chat and stuff on my schedule. I'm very behind because I have a very active toddler at home. So, okay, cheers. Yeah, what are the current approaches to beat the Adam method? Well, there's NADAM, there's BADAM, there's Adam W. So it's really just variations on it because we don't understand how it works. And so if we don't understand how it works, all we can do is like, we just prod it. And so we just do grad student descent to try and find variations that work. And that's been very effective. Like Adam W was the baseline used in the competition variation on it with clever step sizes. But the goal of this work was to try and give us like a new path of attack. Yeah.
Why Adam works in language models? So is it also because the data modality itself? For example, for the languages, you are basically using text. Basically, it's discrete values. You have a finite combination of your text. For vision, it's basically continuous values. The data is kind of like infinite. So is it this difference? Do you think it may cause the difference?
Yeah. Okay. So the question is the gap between Adam and SGD possibly also due to the data itself? Because vision data is continuous, text data tends to be discrete and also very sparse. I bugged Fred to make a plot of this to try and tease apart which factor is stronger. I think they're both contributing, but it seems like the label factor is the more dominant factor, but it is possible that we need to tease apart the answer to that question. So, yeah.
If all we are trying to do is find the bad step size, but how about we kind of model like LSTM or get like the bad step size?
Yeah. Okay. So the question is kind of related to this hypergradient descent idea, and the question is, can we learn to learn? Can we actually use our machine learning algorithm to learn what the algorithm should be? And there are lots of works on this. It looks kind of promising, but it's also like pretty expensive.
Yeah.
Right. I want to keep my O of D cost. Like I'm talking to some of these people in industry, and they don't like Adam because the constant factor in Adam is 16. It's 16D is how much memory on the GPU I need, and 16 is a problem. And so if you're talking about learning to learn, that's your budget, right? It has to be less than 16. So you're not talking about like a big neural network or anything like that. And then there's also the issue of how do we guarantee that it generalizes to a new optimization problem and so on. So I don't want to rule that out in the future because like hypergradient descent came back, as I mentioned on the last slide, with like a provably good way to do it, even though I've been saying bad things about it for 10 years. But learning to learn is still not ready for prime time yet, but good PhD topic still. Yep. Sorry, reducing in Adam? Oh, there's tons of works on reducing the 16 factor in Adam. One of my PhD students is working on with it. She's got a really nice method. They reduce it to like 1 point something, like less. You can get it down to less than 2 with like not too much performance hit. So it is possible. And there's LoRa and Galore and all sorts of different ways trying to reduce that 16. I'm from like a computer science background, so I don't like care as much about constant factors. So it's like 16 is like, well, just make bigger hardware, and then that's not a problem. But of course, when you make bigger hardware, people want to make bigger models, and so people really do care about this factor of 16. But it's not something that I get really excited about. Yeah.
Adam, like compared to SGD, is quicker at learning the like outliers or like rare features. Could it be the case that it somehow learns a different model, like it's better at memorizing versus like understanding, like finding some simpleton data, something like this?
Yeah. So the question is, because Adam is learning these low frequency classes faster, is it learning a different model? And the answer is like, of course it is, and we don't understand it too well. We had a paper submitted to ICML. Actually, I don't know if I can say we have a paper submitted to ICML because it's like double blind, but there are people who are exploring like the implicit bias of Adam and whether it finds like different models. And it appears that it does have different biases, but that's only explored in a very simple setting. It'd be fun to, if there was some empirical way to ask the question to try and get it like the more complicated answers than just like what norm is minimized when you train these things or something like that. Not that the norm question is not important, but I'm not going to be surprised if another algorithm minimizes a norm implicitly. You can read the chat. Maybe if there's selected chat questions. It looks like there was a lot of stuff happening on the chat. In class, I usually just designate someone to ask the chat questions for people, and then it seems like I'm interacting with people. I find that if I read this, I just lose my ability to concentrate. Yeah, okay. Lost audio again, sorry. Yeah, hell yeah. Okay. Could the heavy tailedness also be the cause for distillation to work so well? Maybe the SG Adam gap is smaller for distillation. You're making me think too hard today. That's distillation, okay. Okay, I mean, the default answer is I don't know here. Let me think about it for a little bit more. The thing is, I don't have a good sense of how distillation interacts with the frequencies of the class. So I think we'd have to look at that to see. So distillation, if you don't know what that is, you train on the sort of soft outputs of the network. You train on the probabilities instead of the +1, -1 labels. I don't know what that looks like for rare classes and frequent classes. If there's a pattern there, then it could make some sense for distillation, but I'm not really sure. More dense feedback than one hot. Yeah, maybe. So maybe I see. So maybe because every class is getting a gradient, maybe the effective rare class is less important, and we would see the gap get smaller. But I'm not sure. I mean, you have to try these things out. It's like I didn't expect myself to be doing as much empirical work as I am now. But to understand neural network optimization, you have to try stuff out because sometimes stuff just doesn't work the way you expect it to work. Oh, one more. Make it good. Pressure's on.
What's the nature of language models that contribute, Adam?
Yeah, is there any study on the nature of causal models to this Adam SGD gap? The answer is I have no idea. I would suspect not, because they're two communities that don't talk to each other very much. Yeah, no, I don't even know how you would start to ask that question. Okay, thanks everyone.